So, yeah, the goal of the last couple of weeks is to give a couple more topics that are related to things that we've been studying, like randomization or amortization, uh, but aren't trying to radically introduce anything new. So here would be a topic called randomized rounding, which will give us a little bit more practice with randomized algorithms, uh, which is always good. And it's also going to give you a little bit of exposure to linear programming and a little bit of exposure to approximation algorithms, which are both, those could be full classes onto themselves or things like that. But just so, you have a slight sense for when you go on to bigger and greater things. Okay, so, right, so when we did probability, we had three applications, three set, quick sort, quick select, what you're really doing, quick select. And we're going to do actually something building on our three set lecture. So we won't really do the third one. So today we're going to look at max set as well as set cover. And we're going to do both of them based on this paradigm of combining linear programming with some randomization. Okay, and this is an approach used for many problems out there. So, okay, let me explain what I mean. So today's class, to some extent, it's a story of both, P versus NP and using approximation algorithms as sort of a bridge, right? So some of these problems are hard to solve exactly in polynomial time, but they might not be hard to get reasonably useful approximations, okay? And simultaneously, it'll be a question probing the difference between continuous and discrete optimization. And here the bridge is applied by randomization, right? So we are often interested in discrete solutions, yes, no questions, or giving me various objects, right? The world we live in is sort of discrete, but we're going to use continuous optimization to help us with these discrete problems. So, okay, so on the discrete side, right, there's something called a very general class of problems called integer programs. Okay, so what are the main characteristics? So first of all, so this is a mathematical problem of some kind. It's a little abstract, but it's not hard to come up with why they're useful. But you're just minimizing and maximizing, some kind of sum, a linear function, and you're choosing x subject to various linear constraints, like ax less than equal to b or ax equal to b, so on and so forth, right? So all the rules and all the objectives, they can only be linear functions, okay, which is the simplest kind of function you could find in math. But maybe the real important thing is that here we constrain x to be integers, right? So like a very natural case that if I also write x is less than equal to 1 and x is greater than equal to 0, then you're saying x has to be 0 or 1, right? So you can model like yes, no decisions or, choices over more things. And this problem is just super duper NP hard. We'll see a couple examples, but you can pick any NP hard problem you want. Write it exactly as an integer program without losing information, and that'll show you. But we'll do that in a moment for some of these problems. Okay, so linear programs, here's just the integer program before, it's going to be the same as integer programs, except I'm not going to require this integrality constraint. So this kind of, instead of choosing x to be integers, I'm going to allow it to be any real value. Okay, so now I can choose 0.2, 0.3, 1 over pi, weird things like this, square root 2. Okay, and that's the only difference between integer programs and linear programs, is that the variables are now continuous. Okay, so we've seen one of these before. So max flow could have been written as a linear program, because here I'm just trying to come up with a vector f where I'm assigning some continuous values to all the edges, And my constraints are all very simple. Like what goes in is what goes out. That's a linear system. Or the capacity constraints, I can only put as much flow as there is capacity on the edge. That's also just an inequality. Okay, so that's a particularly nice one. Now, if this is not obvious, okay. I mean, max flow, we had polynomial time algorithms, but it wasn't obvious. It's not obvious that linear programs have polynomial time algorithms, but they do. So weakly polynomial, so only polynomial in the bit length. In fact, trying to get a strongly polynomial running time. Here, like, even though we always think of numbers as being described in bits, but if you're not given the benefit of that, can you still solve it in polynomial time? That's actually not known. Okay, it's like one of the more outstanding problems in computer science. Now, so LPs have a tremendous history. So in 1947, Danzig proposes the simplex algorithm. Do you all know the story of Danzig? So he was taking a graduate optimization class or something, and he came late to class, and the teacher had some problems on the blackboard, so he wrote it down for the homework and went home. And one of the problems was trying to come up with an algorithm to solve linear programs. So he went home. He had some exposure to this stuff from his army time research. This is a little after World War II. And so he came back and he turned in this algorithm saying, okay, it was really hard, but here's the answer to problem one. And the professor's like, oh no, that was actually like a big open problem. So he kind of accidentally for homework invented this thing called the simplex algorithm, which isn't actually polynomial time. You can come up with weird examples. I won't go into the algorithmic details, but it turned out to be incredibly practical. Okay, so it wasn't too hard to code, even on like vacuum tubes, and this just became like bread and butter for all operations research through, 1947. So this is like all through the Cold War and things like this. Okay, so all these people are just writing linear programs and solving them with simplex, and many people are still quite happy with simplex. They say, why do we even bother? That said, it was a major outstanding problem to try to get a polynomial time algorithm. And so that was resolved by a Russian mathematician in 1979. So there's a 32-year gap where a certain corner of the world is completely running on the simplex algorithm. Everyone wants a linear program, to run in polynomial time, but it took a little while to get there. So the ellipsoid algorithm is based on some high-dimensional geometry, something called John's ellipsoid theorem. And so this at least established in principle that you can get a polynomial running time. Okay, but it wasn't actually very practical. And a slightly more practical one comes out in 1984 by Carmarker, who was, I think, a graduate student at Berkeley at the time. Something called interior point algorithm, which looks a little bit more like maybe the continuous optimization were exposed to more machine learning, so they would kind of set up potential functions that get really bad if you violate the feasible constraints of the linear program. Like it shoots up exponentially as you get closer and closer to the wall, and trying to sort of finagle this, over time. So those are the three main algorithms. There's actually still a lot of developments going on in this area. And of course, this problem of trying to get a strong polynomial time algorithm or proving it's impossible remains an outstanding one. So for example, our max flow algorithm, like Edmonds Karp, was strongly polynomial time. So we didn't even care about like the bit precision of the capacities. Assuming we can just do arithmetic and constant time, then the algorithm always terminates strongly polynomial time. This we don't know how to do for linear programs. Okay? But for all practical purposes, we can solve linear programs. You just download something from the internet. It's probably running simplex, some combination of its simplex and interior point methods. Often it's like the first half of the interior point, they switch over. Yeah. Okay, so what's the difference, right? Integer programs, this is sort of what we've been doing all semester, these discrete problems. Okay, linear programs, completely continuous optimization. Okay. But the difference is that integer programs are NP hard and linear programs are polynomial time. And the question we're going to look at today is whether we can use these polynomial time linear programs even though they're not exactly what we're looking for, maybe as a clue towards better discrete solutions. Okay, so here's the high level approach, and this is a pretty robust recipe. So you start with some problem, independent set or something. You model it as an IP. Just say, oh, taking a vertex, it's a 0, 1 variable or something. Something like this. This is not too hard. We'll do a couple examples. And then you take the integer program and you just relax it to a linear program. You say, okay, it doesn't have to be 0 or 1. You can take anything between 0 and 1. And you give it to your black box, your LP solver, and it'll give you an optimum solution to the LP. Okay, so that's great because it's optimum. So like the objective value is going to be very good. It's going to satisfy all the constraints. The only issue is that these are not discrete values. You wanted yes, no answers or something like this, and you're getting like a 0.3, and you're like, what the hell does 0.3 mean? And so trying to take your continuous answer, turn it into a discrete one, that's called rounding. Okay. And we'll just explore some randomized approaches to rounding, but there are many, there's a whole collection of techniques here. Okay. So one thing nice, right, is that we know that X is a really good solution because all I did was relax the optimality, the integrality constraint. So so in other words, the objective value here is always going to be better than the objective value here, or at least as good, right? Because anything that's feasible for my original problem is feasible for the LP. So my LP solution will only be too good to be true, which means that actually I always have some bound on opt. So if I can take X and turn it into a feasible integral Z and maybe lose a factor of 2, the value gets worse by a factor of 2, but it's feasible now, I know I have a 2 approximation because X was already at least perfect and you only lost a factor of 2. So you also get this very nice baseline. Okay. So often in practice, actually, you can take X and do much better than sort of the worst case bounds will get and say, oh yeah, the worst case bounds was 2, but I can just compare my integral solution to my continuous one and see, oh, I'm actually off only by 10% instead of 200% or something. Okay, so good. So let's just see this in practice. So we'll look at SAT again, our favorite problem. And not so long ago, we did this very silly algorithm where for 3 SAT, we just flipped coins for all the variables, and we got a 7/8 approximation, right? And that was really a demonstration of linearity of expectation, okay? And kind of cool, we can also de-randomize it. And yeah, so the key part of the analysis was really just recognizing that we only wanted the average number of clauses that are satisfied. That allowed me to analyze them separately. And then it just actually came much easier from linearity expectation. Okay. So, okay. So that time we were looking specifically at 3 SAT, and we could have looked at 4 SAT or 5 SAT or specific K, because the number of variables in each clause determine our odds of satisfying it. Okay. Now, right. Now we're going to look at formulas that can mix things up, right? One clause has 3 variables, one clause has 5, one clause has 2, maybe a clause even has 1 variable, things like this. And I'm trying to satisfy as many clauses as possible. So, okay. All right, so if we took our silly coin flipping algorithm, right, and I did it for all sorts of k, not just 3, then for k equals 1, that means each clause has 1 variable. That's kind of silly. Our coin flipping algorithm will get 1/2, right? For a clause 1 variable, probably 1/2, you get the right toss. For 2, you'll get 3/4 because you would have to get like tails to get a clause wrong, right? 3 SAT we did together. You need 3 bad coin tosses in a row to get a clause wrong. And then 4, 5, in general for k variables, you'll get 1 minus 1 over 2 to the k, right? Because you need k straight bad coin tosses to mess up a clause. Okay, now what's the best approximation factor this will give you, this algorithm where you just flip coins, for max SAT in general? Or what's the worst case? Or what's the worst entry in the table? Yeah, 1/2. Wasn't a trick question. So it's just 1/2, right? So this is like sort of pathetic because you could solve k equals 1 exactly, right? But of course, our algorithm isn't even looking at the formula or anything like this, and it only gets 1/2. Okay? And sort of one thing that's going on is that our algorithm actually does better when k is large, which would seem like more complicated formulas with bigger clauses. Somehow we can get a better approximation ratio, and we're really struggling on k equals 1 and k equals 2. K equals 2 we know how to do exactly, or at least, sorry, we know how to do exact 2 sat. We don't know how to do max 2 sat, that's true, right? But still, we're doing worse on smaller k, even though you would think those formulas should be kind of simpler. Okay. So, okay. So we're going to try taking this general approach. We'll try to write down an LP, and then we'll try to round it and see if we can beat 1/2. Okay? So the first step is to try to take our max sat problem and write an integer program for it. Okay? So I've already set up 95% of it for you. Okay. Oh, I should have actually erased the objective, but that's okay. So here are my variables. I have one variable zi for every clause I. And I have one variable yj for every variable j. And how I'm going to kind of semantically map it is I'm going to think of xj equal to 1, or yj equal to 1 if I set xj to be true. Okay. And I'm going to set yj to be 0 to mean xj is set to be false. Okay. So that's how I'll kind of try to interpret my integer program. Also with the clauses, zi is 1 if I'm satisfying the ith clause and 0 otherwise. Okay. So the objective is I want to satisfy as many clauses as possible. So I'm trying to maximize the sum of zi's. Okay. But we need some kind of constraints. Otherwise, I would just set all the zi's to be 1. That's not very helpful. So this is the part I've left blank for you. Or we can work through this example down in the bottom right. But for each clause ci, I need some kind of constraint that prevents me from setting zi to just be 1, unless there's really some, assignment for it. Right? So I need to bind the clauses to the assignments. Yeah. Yeah, let's do the bottom right example then. Can you see? Yeah. Well, I guess zi is greater than equal to 0, luckily, is kind of already here, 0, 1. Okay, so zi is less than equal to 1, y1 plus, okay, we'll come back to this, y2 plus y3. So if I set x1 to be, so if I set, okay, so this is not, there's something missing here. So right now I could set y1 to be 0, y2 to be 1, and y3 to be 0. And then I can set z1 to be 1. Even though I have true, false, true, false, right? And false, true, false should not satisfy this clause. So we only have to figure out there's something off a little bit about x2 bar. So it's not y2. Yeah. Oh, absolute value of y2 minus 1. So technically we're not allowed to use absolute value because that's not a linear function anymore. But you're on the right place. I mean, we just want to modify y2 to something awfully similar. So you should only be able to get a point if you set y2 to be false, right? Right now we're getting a point if you set y2 to be true. Yeah. Yeah, just 1 minus y2. That's all. So now when I set y2 to be false, I get that 1 point here, and you're allowed to set z1 to be true. All right, so that's not too big a deal. So that's what this clause will look like. So for a particular clause I, I'll sum over all the variables where xj appears as xj in the clause, and I'll add yj. For all the variables xj where not xj appears in the clause, we'll do 1 minus yj. Okay? So the only way to set zi to be 1 is that you get 1 point from one of these, which is to say you have one of these variables. All right, so good. So we can take that integer program, we turn it into a linear program, and we don't do anything different except now I say that the y's can be any value between 0 and 1. Okay, same with the z's. So it's just a fractional version of the same problem, the same model. Okay. So putting them side by side, the only real difference is that the left-hand side, which is exactly our problem written in a slightly obtuse language, is NP hard. The right-hand side is solvable. You can get solutions to the right-hand side. The only problem is that you're going to get like yi is equal to 0.5, and it's like, okay, what does that mean? Okay. So one thing to point out is that we've already said this before. So because the linear program is a relaxation of the integer program, that means anything feasible here, satisfying all the constraints, would also satisfy the constraints here. So the objective value on the right-hand side can only be better. Okay, so the optimum value on the left is at most the optimum value of the right because it's a max problem. Okay, so I should have erased this. Okay, so we can feed this into our LP solver, some polynomial time black box, and we get this optimum solution, and now we just have to figure out how to turn it into some actual assignment. Okay, so here's our basic predicament. You're given all of these yi values, right? And they're all 1 for every variable. We know that yi equals 0 is supposed to mean you set it to be false. Yi is equal to 1 is supposed to mean you set it to be true. But the issue is that you're given these like fractional values, something in between. Okay, what the hell am I supposed to do with yi equal to 0.33 or something, right? So we want to take the y's, we want to convert them into actual true-false choices for our variables. Okay. So I wanted to give everyone a chance to suggest ideas because once you see the solution, yeah, you won't get a chance to guess again. Any ideas? Yeah. Yeah, so the LP is going to give you these fractional values for all the variables. And you want them to turn them into actual xj is equal to true or xj is equal to false decisions. Okay, like if it's bigger than 0.5, round up. Okay, so we can do something like deterministic rounding, right? So it's like, oh, if it's at least 0.5, we'll round up. Oh, okay. Good, good. Okay. So let me just do one more bit of rhetoric. So I think maybe the crucial thing is like, how do I interpret a value of zero point 0.5? Right? Even your deterministic rounding, it's not even clear what to do with 0.5. Should you go up or down? I think we do 0.5 is what I learned at elementary school, but it's a bit arbitrary. So Uh, right. So to get to the suggested point, I feel like when I was in like high school taking some English class, they tell us about these Greek philosophers who would ask a question like, "What is half a chair?" Right? Like if it has two legs, it can't really stand. Like does it cease to be a chair? Right? And this is like, okay, how do I interpret a variable that's half true and half false? Is how I think about it. And probably is going to actually give us an answer to this, right? Answer to this chair question. Half a chair is a chair that's there half the time. Okay? We're going to interpret y1 equals 1 half to be a variable that's true half the time and false half the time. And on average, it looks like 1 half. Okay? This actually applies to a lot of other fields, economics, physics, and so forth. Okay. Can you interpret as saying that this variable doesn't matter as much? Well, it's a free country, but it's not clear. So the LP is just trying to optimize something, and it's just find some balance point to be setting it to be 1 half. It doesn't mean, for example, maybe it's a really important variable, but like from a certain myopic point of view that the LP sees, which is based on some, gradient of some convex program, it's not clear if it's better to do y1 to be true, or it could be really important, but just like really strong arguments on both sides. So it's not clear to me that like y1 equals 1 half is the LP telling us it's not important. It's just telling us it's very hard to decide. Yeah. Okay. So this is our algorithm. It's very simple. For every variable xj, I'm going to independently set it to be true with probability yj. I'm going to set it to be false with probability 1 minus yj. And I'll do it independently. So it's another coin tossing algorithm, but this time it's not oblivious. I actually look at the LP and look at the formula to some extent and use the LP to generate probabilities for the coins instead of just doing 1 half. All right, so to analyze this algorithm, we're going to take a similar approach to before, where we'll just focus on one clause at a time, and then we'll put everything together. So, okay. All right, so now here is the claim and really the exercise in randomized analysis for us. The claim is that a particular clause Ci is satisfied with probability at least 1 minus 1 over e zi. Okay, so zi is the value assigned by the LP for that clause. Okay, and our algorithm is based on the yj's. And we're going to try to show that every clause is satisfied with probability, not quite zi, so you're losing something, but, within a factor of it. 1 minus 1 over e is like 0.68 or something. Yeah. Okay, a little more than 2/3. Okay, so what would be the first step in the analysis? Well, if we harken back to 3-sat, I think oh yeah, sorry. Okay. So maybe just as a first step, when we were doing 3-sat earlier, it was a little bit easier to think about what are the odds we don't satisfy the clause instead of the odds we satisfy it. Because we know we have to have like bad coin tosses and stuff like this. So we're going to take that approach and analyze the probability that the clause is not satisfied. Okay. And okay, so what is the probability that Ci is not satisfied? How would I write this out? Yeah. Yeah, it's this product over, it's a little bit messier because it's not necessarily 3 variables. So let me parse this slowly. I'm summing over all the variables xj in the clause, and the odds that I get the wrong coin toss, the tails, is 1 minus yj, right? So I have to get bad coin tosses for all of them. So for these, each one is 1 minus yj. And if xj bar appears in Ci, then a bad coin toss is heads. that happens as probability of yj. Okay, so this is just writing out. I know that each variable xj flips heads with probability yj. So 1 minus yj is tails, yj is heads. Okay. Good. Now eventually I want to get this to zi. Now, okay, good. So the question is, what do we do next? Now, maybe as a bit of an idea, I want to eventually get to something related to zi, right? And I do know that the zi's are connected to the yj's because, the sum of yj's and 1 minus yj's over the variables in the clause is at least zi. So that's the connection we want to make to kind of pull out zi, which is meaningful in terms of how many clauses we're satisfying. But I think one basic obstacle is here I'm looking at a product, right? And I know how to connect it via a sum. This happens a lot in this area, okay? And the question is, how do we address this analytically? So I have this product of terms. I really would prefer a sum of similar terms. Take the log. That's not bad, but you're going to get a sum of logs of terms, and you would still prefer some kind of sum of the terms directly. But I like the style of thinking. So taking the log is not bad, but then I wouldn't quite know what to do with log of 1 minus yj and plus log of yj and things like this. And the answer is awfully similar to log, though. It's almost the opposite. Okay, so we're going to use the world's most useful inequality. So if you plot 1 plus x and e to the x, at 0, they're both equal to 1. But actually, e to the x always grows faster because the derivative is e to the x, right? It always grows faster in the positive orthant, and it grows slower in the negative. Okay, so you actually always have this inequality: 1 plus x is less than or equal to e to the x for all x. Okay, this thing's like super useful. It underpins a lot of stuff out there. So if we apply this, I've applied this to every term. So 1 minus yj is less than or equal to e to the minus yj. Yj, which I can think of as 1 minus yj, okay, is less than or equal to e to the 1 minus yj. Okay. I'm missing a negative sign. Okay, good. So this is great. What can I do now? Yeah. So this product of exponentials I can sum up in the exponent, right? So this is very nice. So again, I'm missing. Got the sign wrong here. Okay. So I just convert the product into a sum, right? So now what? Yeah, so this is negative of the sum from our LP. Okay, so I could have written it slightly different like this. Oh, that didn't work out great. Okay. There could have been a parentheses around here and a plus sign. And there you get that thing from your LP. And finally, we get to bring in at long last e to the negative zi. Okay. So we're getting closer because at least zi has entered the picture. We started with the y's. It was this big messy product, although this was exact. And then we did this inequality, right? And at least we're getting closer because it's the zi. So now we need to show that e to the negative zi is at most 1 minus 1 over e zi or something. Okay. So any ideas about how to address this step? Where do we go from here? the log of both sides. Well, there's only one side at the moment. It's e to the minus zi. No, we're going to have to use another inequality. So here we're going to use the fact that e to the minus x is a convex function. Right, so here I've plotted, maybe I can zoom it bigger, right? The function e to the minus x, right? Which is some curve that goes down. All you really care about is the fact that it's convex up or something, right? So it looks like a bowl. And that means if you draw a line between any 2 points, the whole line will lie above the curve. Okay? So if I look at, where zi is between 0 and 1, okay? And so e to the negative zi will be at most, the equal place on that line. That chord, is chord the right name? Anyway, right? This red line here. And that value, that's just interpolating 2 points. I know that e to the 0 is 1. I know that e to the 1 is e, right? And this point in the middle, you're going 1 minus zi this way, and then zi that way. Okay. So you get this. So that gives you this inequality down here. It's a bit more quantitative than usual. I'm not expecting you to kind of master this kind of thing. That's okay. But ultimately, out comes 1 minus 1 minus 1 over e zi, right? And here we're looking at the probability that ci is not satisfied. And we got 1 minus the thing we're looking for. The probability that it is satisfied is 1 minus this, and then you'll get 1 minus 1 over e zi. Okay? All right, so I recognize that this is a bit more quantitative analytic than we're used to. That's not so much the point of emphasis is not to memorize these techniques, but just to get exposed to this style. Okay, and you can see, I do think that going from products to addition just with 1 plus x less than or equal to e to the x is something that you may see in many different places. So it's not uncommon, in things beyond the scope of this class, where you are going to be faced with things like big products and you need to deal with it. Often in a place where summations make more sense. That's not uncommon, not only in approximation algorithms, but elsewhere. Okay. All right, so you need a little calculus sometimes. Okay, so once you get through that, this part now, the claim is, okay, so that was for one clause. One particular clause is satisfied as probability 1 minus 1 over e zi. Okay, it was a little messy, but now it's in a box. The claim is now that the expected number of clauses we satisfy is at least 1 minus 1 over e times opt. Opt is the opt really, best possible. So that would be nice, right? That's much better than 1/2. So how do we do this? I know a particular clause is satisfied with this probability 1 minus 1 over e zi. And now we want to claim we satisfy at least 1 minus 1 over e times opt. That'll finish our proof. This part is not as tough as the last one, which was a bit analytical. Yeah, we sum that, and how do we sum them all up? Okay, excellent. So we can set up variables. AI will be 1 if the ith clause is satisfied, 0 otherwise. So this thing is the expected sum of AIs, which by linear of expectation is going to sum up the expectation of each AI. And for each AI, this would be okay, Some of you are saying this secretly. 1 minus 1 over EZI. That's what we showed. Okay, now here's the last interesting conceptual step. How do I relate this sum of ZI's to opt? We can take the constant out. Okay, I'll take the constant out. Okay. So how do I deal with the sum of ZI's? I think that's right, but just one bit's flipped. So the optimum, okay, so we want to, well, you know that we should get the sum is greater than equal to opt, just a pattern match. But the question is why? Yeah. Yeah, because of the linear program, right? So these ZIs are coming from a profit that gives us a perfect solution to an easier problem. So this term is at least opt. Okay, which I think is really the key point, trying to figure out how to take an LP and sort of try to interpret its output as suggestions for a reasonable solution, right? And being able to relate with the LP, the outcome with the actual true optimum value, right? This is great because we don't even know opt. It's MP hard to figure out opt, right? But the LP gives us some handle on it. Okay? So it's kind of a conceptually interesting thing. Okay, so this last part, yeah, yeah, we're trying to maximize this. Well, we lose something here, so we get at least 68% of opt. We would love to get 100, but that's MP hard. But we can at least get 68% or something. In the worst case, right? Maybe your algorithm outperforms the worst case. Yeah. Okay. So the question is, can we do better? And we're going to find a way fairly quickly. So this will be a fun part. Okay. So, okay, so we showed that each clause is satisfied as probability 1 minus 1 over EZI, right? But this is like a little bit clumsy. For example, what if CI has one variable? Then what's the probability we satisfy it? So if like CI is equal to x1 or something, then the probability should probably be y1, which is whatever we assign to x, that variable x1. And the LP is probably going to set z1 to be that value. There's no reason to make it lower. Okay? So you get exactly zi for one variable. Okay? So 1 minus 1 over e is a bit clumsy in this regime. What happens if you have two variables? Okay, let me just go through this quickly in the interest of time. So two variables, in fact, our algorithm analysis is a little bit clumsy as well. So we handled the general case and we did a good job, but some of these special cases, we left something on the table. So if, for example, CI is equal to x1 or x2, the probability of not satisfying it would be 1 minus y1 times 1 minus y2. Here we'll use something called AMGM, which is sort of like this SAT question. You have a certain amount of fence. Well, how do you get the most area? Things like this. I don't know if you remember. Okay. So this product is at most this average squared by the arithmetic mean, geometric mean inequality. And now you start taking this. So y1 plus y2 is zj. So I put that in. Okay. We'll have to do some convexity again. I thought there was going to be a picture here. Oh, there's no picture. That's okay. But by convexity, you're going to get something like this, just like we did before with the tangent line above the curve, and you'll get 1 minus 3/4 dj. So the point is you can get 3/4 if there's two variables. Okay. So again, that's better than 1 minus 1 over e. So why am I making this point? Okay, so we have two algorithms, right? One algorithm is just to flip coins, randomly, and the other algorithm is this more LP based flipping. Okay, and if we look at like our performance, so as we mentioned before, like a clause with 5 variables will be satisfied with probability 31 over 32 and things like this, right? And for the LP, we have roughly this column. Okay, the LP is going to satisfy a clause either with zi or 3/4 zi or at least 1 minus 1 over e zi for the other ones. Okay, now if I like ran these two separately and I took the average, right, and said, oh, what are the odds? What is the expected number of times, so to speak? So on average, every type of clause, no matter what k is getting at least 3/4 zi. So 1/2 is at least 1/2 zi. So 1/2 plus 1, that would be at least 3/4 on average, right? 3/4, 3/4, 3/4 on average. Here, 7/8 plus 1 minus 1 over e, that's at least 3/4. So in a certain sense of the word average, okay, you're getting at least 3/4, okay? But that's the average over two different algorithms, okay? So now here's my question. How can you get one algorithm that will get you a 3/4 approximation? Does that make sense? So sort of some average of two different algorithms would seem to get 3/4 on average, right? But you can only run one. So any ideas here? So our last question and then we're done. So I have two algorithms that it feels like together they should get 3/4. But I can only flip coins by one of the two rules. How can I combine these two algorithms so I can get that average performance, so to speak? Try guessing. This is more guessable than you think. Okay, try taking the average. That won't quite work. Yeah, meshing the averages won't work. There's a different answer. We won't rewrite the linear program. The answer is simpler than that. Okay. I'm going to flip a coin. If it's heads, I'll run the first algorithm. If it's tails, I'll run the second. And then everything's going to work out because of linearity of expectation. Okay? So that's it. You're going to flip a coin. If heads, you do one. If tails, you do the other. And that's how you can get the average of the two columns. For each clause, if it's heads, it's getting something in expectation. If it's tails, it's getting something else in expectation. You take you sum up the two things by linear of expectation, you get 3/4 for every clause. Okay, so that's a nice trick that you can only do with randomization. You can do half and half. Okay, all right, and that's it. Thanks, guys. Okay, so so we started this last time. We started talking about approximation algorithms, randomized algorithms based on the LP. And I have just one more example. It's actually maybe a little easier than what we did last time. I don't know. But just one more basic problem, one more example. And then I think in the second half of class, which usually works out to like the second or last third or something, I'm hoping to talk a little bit about hash tables. So the end of today and Friday will be about hash tables and also a cool application called the heavy hitters problem, which uses hashing because I feel like you should know a little bit about hash tables, seeing that is probably all you use. Okay, so all right, so let me just remind us the high level overview of this lecture. So again, when we talked a little bit about linear programming as this polynomial time oracle using randomized rounding to get the discrete solutions we want. So, right, linear programs are just simple problems that look like this. An example that we previously had was max flow. And the key point is that they're polynomial time solvable. So they would seem to describe our problem really well, except for the integrality constraint. It can output real values. So it doesn't quite get us exactly what we want, but at least it gets us something in polynomial time. And then can we take that, turn it into a discrete solution? So this is the general recipe. You take your favorite problem, you write down an integer program. This is usually not too hard, like the variables just correspond to like yes, no decisions, things like this. You know, you have to do this, you have to do that. That might be like a covering constraint, something like this. You just relax it to an LP and you put it into your black box. It gives you some continuous solution. Not exactly what you're looking for, but maybe a suggestion towards the correct solution. And you just have to figure out how to turn those fractional values into zeros and ones. Okay? And this is especially useful for these MP hard problems where you're not going to get, at least barring essentially a miracle, you know, a polynomial time algorithm for discrete solution. But we can still use the LP to get reasonable solutions. So we did max that last time. And what we did last time was we took our silly 7/8 approximation algorithm, just flipping coins. And when we tried to make it work, well, we wanted to develop an algorithm for maxat in general, which has a variable number of clauses, the variable number of variables, arbitrary number of variables in each clause. Okay, and part of the motivation there was that our silly algorithm actually worked really well when there's lots of variables in a clause because you have to get really unlucky to get it wrong. But it really struggled on silly things like clauses with one variable. Okay, so we considered the LP-based approach where we wrote down the integer program for sat. We wrote down turned that into a linear program, okay? And the linear program for each variable was giving us a fractional value saying whether or not to set it to be true or false. And our simple algorithm was, okay, so the predicament we faced was, I give you all these fractional values for every variable, and I want to turn it into a true-false assignment. Okay? And what we found to work was to interpret the fractional values as probability. So if the LP tells you it should be half true and half false, that doesn't make any sense on the face of it. But we're going to interpret that as, oh, let it be a random assignment that's true half the time and false half the time. Okay. We did some analysis on this. We showed that each clause is satisfied with probability 1 minus 1 over E times ZI, which is the value assigned by the LP. There was a little bit of more analysis than we're used to. I don't want to get too distracted by this, but this is a certain style of a certain subfield of computer science. I'm sure you'll see some of these inequalities in other contexts too. And once you did each clause, then we do linear of expectation as usual. Okay. And that at least got us a 1 minus 1 over E approximation, which is better than 1/2. All right. And then the fun thing is like, okay, so if we look at our LP algorithm, it does a little bit better for the small clauses. So for clauses with one variable, it actually just gets ZI. With two variables, it gets 3/4 ZI. Okay. And so we found ourselves in this situation where we have this oblivious algorithm which does really well for large K and struggles when there's only one variable per clause, two variables per clause, things like this. Our LP algorithm is kind of mediocre for large K, gets 1 minus 1 over E, but it does better for the small values of K, right? It's particular for 1/2, for one variable. And so at some level, it felt like the average of the two performances will get you at least 3/4 of every clause, right? And yet we were stuck at 1 minus 1 over E. So can you get 3/4? And that's what we kind of closed the class with. And the trick is, as someone pointed out, so the issue is I would love to kind of run both algorithms simultaneously in some sense, right? I know the average of the two algorithms should be good, but an algorithm, you can only choose one. So what we'll do is we'll flip a coin. If heads, we'll run the silly algorithm. If tails, we'll run the LP-based algorithm. And then you work through the linearity of expectation for each clause, and you're satisfying 3/4 ZI for each clause. Okay, so that's a really cute thing, right? We use a coin toss to sort of simulate running two algorithms and taking the average while only actually running one of them. Okay, but analytically, you're getting the benefit of the average of an algorithm, even though you can't average an algorithm, right? You can be like, oh, the computer takes one step here, one step there. That would be a nonsense. Yeah, so that's kind of neat. All right, so I had one more basic problem. We won't do the last one. Set cover, which is also just a basic problem that hasn't come up yet. Okay, so set cover is a popular optimization problem. So here's the basic setup. So I give you a bunch of points and a bunch of sets. Okay, and you want to choose the fewest number of sets so that you cover all of the points. Okay, so I don't know, you're a cell phone company and or cell phone communication company, and there's all these people you want to provide coverage to. The cell phone towers, are some circle with some radius, and you want to place the fewest number of towers to cover everybody, right? So that's like a basic thing. But you're just trying to take a few things to satisfy some requirements. So take this one here. I know it looks a little chaotic, but I got red circles representing sets and blue dots representing elements. What's the fewest number of sets we need to cover all the dots? Is this one too hard to stare at? Okay, I have some approaches. So there's some sets that we know we have to take because they're the only ones covering certain points. So those are at least these ones. So I'll make that a different color. I'll make it, any favorite colors? Yellow. Oh, wrong, wrong. Okay. Stroke. Okay. Yellow. So those sets we definitely have to take because there's points where there are only sets covering them. So given those four, what's the best we can do? 6. So just two more, I think. So like one possibility is to take, I guess, this one and something to cover the remaining points. And then I guess either of these are okay. Okay, so that would be 6 sets. Okay. So that's the goal, it's minimum. Now, it probably won't surprise you at this point in the class that this is NP hard. So we're going to try to give a reduction from SAT. I suppose there's a couple of choices, but we're going to do one from SAT. And just for old time's sake, I thought I would let you guys try to think of a reduction. Yeah, okay, so I think this is right. So sets you're taking, right? So the decision is at the set level, taking sets, and in set the decision is at the variable level, assigning variables. So somehow like assigning x1 to be true should correspond to maybe some kind of set, right? So maybe uh, assignments, individual assignments, something like x1 equals true should correspond to some kind of set uh, S1, maybe I'll call it S1, x1 is equal to false. I'll call that T1 or something. And and in set cover, there's variables. I mean, there's points you're trying to satisfy by covering them, right? So the points represent requirements, and in set, the clauses represent requirements. You need to satisfy the clauses. So somehow we're probably thinking that clauses should map to points. Okay, so CI might map to point PI. And now what should the sets be relative to what points should a set contain? So a set corresponding to S1, which points do I want to put in it? Yeah, so maybe S1 would be the set of all clauses, or I guess it would be a point PI where X1 appears as a literal, uh, is in the clause CI. Okay. All right. So we've taken a SAT formula, we've turned it into sets and points. Are we done? So I can give it to the black box and it'll say, oh, you need this many sets, right? And then we have to convert that to a yes, no. Oh, yeah. So that's going to come up. So, okay. So we shouldn't be allowed to take S1 and T1, right? Because that's setting X1 to be true and X1 to be false. So we're going to get to that. Let me try to break it down piecemeal since I know the solution a little bit. So maybe first, you take your sets and your points, you give it to your black box, and it says, okay, you need K sets for some K to cover all your points, right? What would be and then you probably want to say, oh, if K is bigger than this, I should answer no. If K is smaller than this, you should answer yes or something, right? For the original SAT formula. Remember, it doesn't tell you the sets, it just tells you the number. So what's a natural choice of threshold? Yeah. hmm Sure. So we're just inventing things, right? So for every variable or every possible assignment of a variable, x1 to be true or x1 to be false, I'm going to think of that as a set. For every clause, x1, x2, not x3, I'll think of that as a point. Okay, so I'm going to make a point. Say, oh, point one is for clause one. Point two is for clause two. So now I've just made a bunch of points. But now I need to decide which sets contain which points. And so what we did, we said, okay, if clause one includes x1, it's like x1 or x2 or not x3, I'll have the set for x1 equal true include the point for clause one. Because we're kind of thinking of choosing the set for x1 to be true, like setting x1 to actually be true. So it'll cover that clause, that point for that clause, because it also satisfies that clause. Yeah, I have a better picture coming up. The only thing is that the picture gives away the rest of the answers. So it'll be clarified, I think, a little in hindsight. So the next intermediate question is, what's a natural candidate for? So black box says you need this many sets. This is the minimum number of sets you need to cover the point, right? It can always, for example, say, oh, 2n, you need all the sets to cover the points. And that's not very useful, right? So that probably should map to no, right? Yeah, okay, but a natural choice is n at least, right? Like, for example, if it said you only need one set, then you're like, oh, then you only need one variable to make everything happy. So like small numbers are kind of mean it's more likely to be satisfied. Bigger numbers are kind of less. A natural threshold, because you're probably thinking, oh, you should take one set for each variable, right? So a natural, at least idea is n. Okay, so maybe a threshold n. So, and this is not, and then we'll come back to this point that was raised. Okay, so if min number of sets, I guess in any set cover, is less than or equal to n, return, f is satisfiable. So if you're able to cover all the points with at most n sets, return f is satisfiable. Okay. Now the issue that was pointed out is, and then if it's more, you turn not satisfiable. So the issue that was pointed out is that the black box is allowed to use S1 and T1, right? And in SAT, we're not really allowed to do that. You can only set X1 to be true or X1 to be false. So we're really close, and we just need a hack to fix this bug. So ideally what you want is that you want the solution to take exactly one of S1 or T1, and exactly one of S2 or T2, and exactly one of S3 or T3 for all the variables. And you know that it's only allowed to take n sets. Yeah. So the point we've gotten to is as follows. So the black box is going to try to figure out if it can cover the things with at most n sets. If, for example, we already know if the minimum set cover is bigger than n, it's definitely impossible. Okay, so actually our no means no is correct. Our current issue is that sometimes we might answer yes, but the black box is cheating because it's like using S1 and T1 in its solution. So that's the main bug we want to address. And as a hint, okay, so as someone, we've already kind of constrained ourselves to solutions with at most n sets in it, okay? And I want to force all the good solutions to have exactly one of the S1 and T1, exactly one of S2 or T2, right? I really wanted to make these choices for each one. We're just kind of one hack away. Yeah. Yeah, so what we can do, okay, so if I can also, so given that it can only take n sets, if I can force every set cover to have at least one of S1 or T1, at least one of S2 or T2, the only way to do that using n sets total is to take exactly one from each, right? And so now, how can we do that? How can I force it to take at least one of S1 or T1 in any set cover? Yeah. Yeah, we're working in set cover, so we're going to add an auxiliary point. That's just going to be, oh, this point's only covered by S1 or T1. Oh, that point's only covered by S2 or T2. So I guess here, so originally here's our clauses. Each of these becomes an element, a point. Here elements means points. Okay. And then our assignments, assigning x1 to be true, x1 to be false, that'll correspond to sets. Okay. So this was our first part of our construction. And in the last part, I add one more auxiliary point for every variable. And what this does is say, okay, I have to either take this set or this set to cover this point. I have to take at least this set or this set to cover this point. Okay. So any set cover has to have size at least n just to cover these n points down at the bottom. Okay. And if it can do it with exactly n, that means it's only choosing x1 to be true or x1 to be false. And it's only choosing x2 to be true or x2 to be false. And it's also satisfying all the clauses. Okay. I won't fully do the if and only if, but then next we say, okay, if it's satisfiable, here's the sets in the set cover. If there's sets in a set cover satisfying this, then it's going to map to a satisfying assignment because, well, I'm covering all the clauses and I'm only taking one from each because of this thing. Okay. All right, cool. Okay, so set cover is empty hard, but we can still try to approximate it. So we're going to take an LP-based approach. Okay, so step one is to write just an integer program. So I've left the most interesting part blank, but let me explain the rest. So we want to take the minimum number of sets to cover all the points. Okay, so I've modeled taking a set as just a 0, 1 decision. Okay, I take it or I don't. 1 means it's in the set cover. So the minimum number would be minimizing the sum of xj's. Okay, but we need to write the requirement. How can I express my one constraint? So I refers to points, points 1 and m, and the sets are indexed 1 through n. As usual, we use the only two letters in the alphabet that sound the exact same and look the exact same. What should the constraints look like? Okay, well, there's going to be one constraint for each point. So what's the requirement for a particular point? I should have at least one set covering it, right? So how would I write that as a equation? Okay, maybe equations are no fun. So I'll sum up over all the sets that contain the point xj, right? This sum needs to be at least 1. And that's all. Good. So that is the integer program. The linear program is just going to take that 0 or 1 decision and make it between 0 and 1. Okay. And yeah, so not a big difference, except a big difference computationally, because this one we can actually solve in polynomial time. So, good. So the LP gives you this fractional assignment, right? It says, oh, you want to think, oh, if it's 1, then you should take the set. If it's 0, you shouldn't take the set. But what happens if it says, oh, you should take 0.3 of this set, 0.4 of this set, 1 over square root 2 of this set? So that's the next question. How do we deal with this? Just round everything up. Okay? So one approach is just to try to round everything up. Okay, so one thing I'll be very worried about is that, for example, if I took my original set cover problem, okay, and I just duplicated all the sets a ton of times, okay, the optimum value hasn't changed, of course, because the duplicates don't help you. But the LP can now do things like assign 0.000001 to every copy of the same set, right? So it'll give teeny tiny values, but it'll still satisfy the linear inequality in the aggregate because there's so many duplicates. Okay, and now you're going to round everything up, right? And so it's going to be much more expensive than your LP solution because you're taking something arbitrarily close to 0, turning it into 1 for all of them. Right? So that would give you a feasible solution, but it might be really expensive. And of course, the solution you output, it will be super redundant, right? Because all these duplicate sets, there's 0.0001 on it. You're taking all of them. Yeah. Given that it's the title of the lecture, we're going to randomly round. And so I'm going to interpret half a set to be, oh, we're going to take it half the time. Okay, that's at least a start. So, good. In fact, maybe there's something you should already have we'll find out. All right, so let's say that I'll call F to be the family of sets I actually take. Okay, so you randomly round. 0.5 becomes 1 with probability 1/2, 0 with probability 1/2, and that tells you which sets to take. Okay, so out of this experiment, you're taking a random collection of the sets. Okay, so we need to analyze, okay, how big is this thing? How many sets did I take? right? And then am I actually getting a set cover? So we'll start with how many sets do I take, which I guess is denoted the size of F. Okay. How do I analyze this? You will not take half the sets because you're randomly rounding. All right, what's the first step? Okay. If you're just like worried about the exam, just know first step will almost always be linear expectation. It's the number one thing I want to communicate. So summing over all sets J, okay, and the expected value of, you could have some random variable that's maybe like, I'll write it slowly. I'll write X, I'll write AJ, okay, where AJ is equal to 1 if Sj, the set J, is added to our collection and 0 otherwise. Okay. So I could have written out a little bit more, but I could have written the size of F to be the sum of AJ's first, the expected value of a sum, and then that becomes a sum of individual expected values. Okay. And now what is one of these for a particular AJ? What's the probability we take the set? Hmm? It's not half, it's xj. Okay. And this sum has a particular meaning. Or where have we seen this sum before? In the objective, right? So this is the fractional number of sets in our LP solution. So this quantity is actually really good. This will be, whatever is the optimum value. In fact, it's the optimum for the LP, which could be less than the integral optimum. Okay. So actually, we get the expected number of sets we take is perfect. Okay. Does that make anyone worried for any reason? Well, yeah, but we know the problem's NP hard. So if this thing is outputting feasible solutions, then suddenly we're solving NP hard problems, which is going to be unlikely. But let's see it play out in a slightly different way. So, okay, so we also need to know if our collection is a set cover. The fact that the number of sets it's outputting is perfect means it probably isn't, but let's see also where it fails analytically. Okay. So, for example, as a starting point, suppose I fix a particular point and I want to calculate the expected number of sets that cover the point. How would I go about it? What's the first step? Well, what's the first step? Okay, good. All right, so we can write AJ to be a random variable. That's 1 if SJ is an F, 0 otherwise. So you're looking at expected sum of AJs over all sets Sj that contain the point I. Okay, so you're just summing over the sets that contain it. And then you get your linearity of expectations. Okay. And as we just saw, what is one of these expected values of AJs? xj. Okay. And now this sum also has some meaning. Where have we seen it before? This is in our constraints. So for every point I, the sum of xj's over sets that contain it need to be at least 1. Right? So we have to fractionally cover the point. So this is at least 1. Okay? So this is good. The expected number of sets covering a particular point is at least 1. In some sense, we're covering each point in expectation. But that doesn't quite mean F is a set cover. What are we really interested in? Okay. Well, okay, so first of all, I don't really care about the expected value. If there's 2 sets, it doesn't really affect me. I just want to know if there's at least 1. So there's a slightly different calculation of what's the probability that F covers I, right? Which is a little bit easier to look at the probability it doesn't cover I. And then we'll start doing something similar to before. So we'll look at all of the sets that contain it and the probability that I don't take that set, right? The only way I don't cover I is I don't take any of the sets that cover it. So those are all 1 minus xj's. Okay. And in same predicament as last class, I have this unwieldy product. The sum of xj's has some meaning to me, but the product's a mess. So what do we do? Yeah. So this is less than equal to e to the, I'm just going ahead and put the sum in, containing I negative xj. That sum of xj's is at least 1. Okay, at most e to the minus 1. So the probability that f covers I is at least 1 minus e to the minus 1, which is like 0.6 something. Okay, 68. Okay, so good. Okay, so we have shown that f will cover each point with constant probability. Okay. Does that mean with constant probability f is a set cover? So to be a set cover, you have to cover all the points simultaneously. Okay, so just to say that f has a 75% chance of covering any given point, it could still be a near zero chance of covering all points. Okay. So that's actually our predicament. Our algorithm actually didn't quite work. Although our objective was great, we never output a set cover. Okay? But it's a really good starting point. I want to take our randomized rounding approach and just make it a little bit stronger. We might give up something on the objective, which you should expect because the problem is NP hard. Okay? So how can I, roughly sticking to this approach, maybe increase my odds that F will actually be a set cover? Okay, so there's at least 2 approaches. One is maybe I can try to repeat. Okay? And the idea is like, okay, I'll cover half the points on the first pass and then half of the remaining points on the second pass, and on average, things like this. And hopefully I only need log n passes. We're going to go in a slightly different direction though. Yeah. Well, yeah, maybe. So such as, can we take into account how many sets cover that point? How many points are covered? Uh, well, some of this is taken into account by the LP. The LP is quite optimizing over sets and stuff. It probably is going to assign more weight to sets that cover more points if it really makes sense to do so. So I think some of this is baked into this LP. So we won't take a strategy that's quite that kind of granular. Okay, so right now we're randomly rounding, but I'm not taking enough sets to guarantee I'm a set cover, right? How can I adjust my rounding to increase the odds of being a set cover? I mean, you get to change it, right? So you get to kind of like rig the experiment. How would you rig the experiment? Yeah, I can try to increase the probabilities, right? So what's one way to try? Yeah, but you can assume all the XJs are arbitrarily small because I can always do this duplicating sets thing. But okay, how do I increase my probabilities? Obviously increasing probability will increase my odds of being a set cover. What's a natural way to do this? Huh? Yeah, so what's an easy way to do this? How do I just lift everyone? Yeah, let me just multiply xj by some big number. I'll take all the xj's and just multiply them bigger. Okay. My objective will go up by the same amount. If I multiplied everything by 10, okay, then it'll become 10 opt instead. We'll have a 10 approximation. But maybe this calculation that led to e to the minus 1, this should start looking like e to the minus 10 and things like this. Okay. So, right. So if we do the linear of expectations again, okay, so one sec. This is a little bit small. So I don't know what I was thinking. So what we're going to do is we're going to figure out a scaling factor alpha after doing the calculations. Okay. Uh, and then we'll just see how it works out. Okay, so alpha is some variable. You can think of it as 10 or something. We're going to multiply everything by alpha and see how it works out. Okay. So now, and also if alpha times xj is bigger than 1, that just means we take it with automatically. So, okay, what is now the expected size of our set cover relative to alpha? So if we do the same thing as before, you're going to get alpha xj when we apply linear of expectations, right? And you take alpha on the outside, and you get alpha opt. Okay. Now, okay, so that's straightforward. Maybe this part is a little bit more interesting. Okay. So let's look at the probability that our set cover does not affect a particular, does not cover a particular point I. Now, if any of those sets that cover I has probability at least 1, because alpha times xj is 1 or bigger than 1, then you'll just take it, right? So you're only interested in the case where all those values are less than 1. In that case, we'll take the same first step as before. So we'll take the product over all sets Sj that contain the point I, 1 minus, alpha xj this time. Okay. And we'll do the same step as before, where we exponentiate things so we can make sense of the product. So we get e to the negative alpha, summing over all sets Sj containing I, xj. Right? This is from 1 minus x is less than equal to e to the negative x for any x. Okay. As we know many times by now, that sum in the exponent is at least 1. Okay. So e to the minus alpha. Okay. So this is great, right? So, if you pay a factor of 10 in the cost, your odds of satisfying a point goes down at a rate of e to the negative 10, right? So you're actually getting an exponential rate in terms of covering everything, okay, relative to what you're paying in the objective. Okay, so 10 becomes e to the negative 10. 100 becomes e to the negative 100. Okay, so it's a favorable trade-off. So if I wanted this to be at most 1 over, say, m squared, m is the number of points, what should I set alpha to be? Alpha is something like 2 log m. Okay. All right, why do I want it to be 1 over m squared? Okay, yeah. Okay, so good. Okay, so any particular element I, as covers probably say 1 over, I can make it super small. A logarithmic factor in m, it's, 1 over poly m. Okay. Now I'm interested in the probability that f is not a set cover altogether, right? So again, we still have the original predicament of, okay, I'm satisfying a particular point with really good probability now. I can even control it. It's a pretty nice trade-off. It's exponentially small in alpha. But I want to make sure I cover all the points simultaneously. So now how do I do this leap? We're going to have to do something I don't know if we've done before, but you've seen before. So I know how to deal with 1 point. And in fact, I feel really good about 1 point. But now I'm trying to deal with all points simultaneously. So you have to be careful because these are not independent. Okay, so that's a real issue, is whether or not you cover 1 point is strongly correlated with whether you cover another, right? If I know I'm covering this point, then I'm taking more sets, I'm more likely to cover another. So it's not independent. You can't just break it up. So that's the issue. So you're in a very dependent situation. I don't think I've put you in this situation before, so it's good to see this. Okay, so you're getting really close. Would it be a sum of conditional probabilities? In fact, we're going to remove the problem. We're going to remove the word conditional. But what's the justification? Okay, so suppose I told you that this is actually bounded above by summing over all of the points I, the probability that f does not cover I. That would be very convenient, right? It's not as strong as independence, because independence would like multiply things and do 1 minus and stuff. That'd be even better. But this is just summing over things, and that would be good because we think this number can be made really small, right? But why am I allowed to do this? Obviously, it's very appealing, it's very simple, it's very clean. I can deal with the rest. But why does that inequality hold? Yeah, so this is the union bound. This is the other thing that is very simple, but is insanely useful because these kinds of situations come up in randomized algorithms. So the union bound says the probability of, say, two events, A or B happening, is at most a probability of A happening plus the probability of B happening. Okay? And the proof is essentially like a Venn diagram, right? There's A happening, B happening, there's some overlap, right? A or B is the area of the overlap if you're throwing darts at a dartboard. And that's at most A by itself plus B by itself, right? Because you're actually not getting credit for the overlap. Okay, so, sorry, hide this. Okay, so this is at most there's m points in e to the minus alpha, okay? And if, like before, we set alpha to be like 2 log m, natural log of m, so you can get like m dot 1 over m squared, which is equal to 1 over m by setting alpha to be, 2 natural log of m. Okay. So what happened? Because of this exponential decay, by just setting alpha to be like natural log of m, I can make these individual things polynomially small in m, like 1 over m squared, right? I just increase the constant in front of the log m, and this exponent increases, right? So it's a great trade-off. And that probability is so small that I can just naively, union bound is sort of a naive bound, right? Just add them up and it's still good for us. So that's the point. That's the point. We can actually guarantee that we satisfy all the points simultaneously by taking the union bound, right? Okay. So good. Right on time. So you get a log m approximation ratio for this problem. Okay. All right. So that's it. Next time we'll do hash tables and this cool application called heavy hitters. And we will use the union bound again, so it won't be such a waste. Okay. All right. Thanks, guys.